everybody. I'm Mark Tewksbury, your host for this program. Our goal is to reveal the methods and materials that turn out the products we see every day around us. There's a whole new world of things waiting for us to discover here on How It's Made. Casein and whey are milk proteins. Researchers are using them to make packaging to seal prepared foods like pizza. The product is a protective film that conserves food longer, in fact up to 10 days longer, without changing the food's flavor whatsoever. How convenient. On today's show, bicycle helmets, aluminum, new technology breaks, lithium battery cells. I like riding a bike, and I also value my life, which is why this solid safety helmet is a must. Not bad looking either. A bicycle helmet is constructed of an exterior shell and an interior one of polystyrene foam designed to absorb shocks. Some designs for bicycle helmets are drawn by hand and with computer-aided graphics. The design has to take into account that it is not on a flat surface but on a rounded one. This creates optical deformities that have to be corrected. Fabrication begins with the exterior shell. This polymer sheet is heated in a heat former at a temperature of 65 degrees centigrade. The mold lifts the sheet and suctions it to fill all the cavities of the mold. This operation lasts about 1 minute and produces 4 shells. Then, when cooled down and hardened, the 4 shells are cut by hand. Ventilation openings are cut with a heated wire apparatus. These openings have been preformed during molding of the shell. The heated wire easily and neatly cuts the polymer. Next step, trimming the helmet to eliminate excess polymer. The circumference is manually cut using a router. The edges are then sanded to even them. It is also possible to cut the circumference of the shell with a heated wire. This operation takes more time but is more precise because of the resulting cleaner cut. Now they're going to fabricate the foam interior that will be placed inside the shell. It's made of polystyrene beads that will expand and bond together. This expander increases the volume of the granules that fall into it. Steam and an agitator let the polystyrene beads expand uniformly. The granules are now ready. The contents of this bin will be able to produce about 20 foam pieces, which will take shape on these molds. The press closes up for the 6 minutes that it takes to mold 4 foam pieces. The particles fuse with steam before being cooled with water. The foam is removed from the mold. Forms are produced for different helmets. Fusing of the particles has welded the granules to one another. Depending on the helmet model, openings have to be made with this heat iron to allow for installation of an air vent accessory. All that remains is to make the adjustment pads, cut with this press-powered stamper. The adjustment pads are held in with Velcro to allow easy adjustment of the helmet. This allows the cyclist to change the foam pads for greater comfort. Inserting the straps calls for good manual dexterity and takes only a minute. The shell and the polystyrene foam liner have to be joined. They're adjusted one inside the other. then solidly secured with adhesive tape. The helmet is now completed. And now it's ready for packaging. The safety helmets have to be certified, guaranteeing their safety, and conformity tests are done. At least one helmet in 500 will undergo this destructive test. Here it drops vertically onto a piece of steel. This facility can produce up to 4,000 helmets daily in hundreds of models and over 500 variations. Look around and you will find it. Used for everything from jet planes to cans, aluminum, light and strong, has earned its reputation as the wonder metal of the century. Aluminum, so widely used today, and the world's most abundant metallic element, does not occur in a natural state. The most available source of aluminum is actually bauxite. Bauxite is mainly mined in tropical countries and carried by boat to the Quebec port of La Bay. The aluminum atom in bauxite is bonded to oxygen molecules. These bonds have to be broken by electrolysis to produce pure aluminum. Bauxite is carried by rail to the plant where it will be crushed. Then, through a chemical transformation called the Bayer process, alumina is extracted. This is then roasted in calciners to eliminate all moisture. This is alumina. It is transported by rail to the reduction facility. This plant has 432 pots in which a powerful electric current will be passed to produce electrolysis. An overhead crane dumps alumina into the pots. Then the electric current from the anode placed in the alumina passes through the alumina, which we see here right at the bottom of the pot. Via the process of reduction of the alumina at 950 degrees centigrade, the anodes lose volume and will have to be replaced. It's a continuous operation. Each anode has a lifespan of about 20 days. Spent anodes are recovered from the pot with this overhead crane and carried off to be recycled. They clean the aluminum rods, which will then be reused. Here we see the crust formed atop the anode. When the anodes are replaced, the accumulated impurities have to be recovered from the top of the pots. This is accomplished with these pincers. Then a new anode is inserted into the alumina and electrolysis continues. The electric current breaks the molecular bonds. The heavier aluminum collects at the bottom of the pot, while the oxygen bound to fluorine is released as a gas which is drawn off and treated. The liquefied aluminum remains at the bottom of the pot. It has to be recovered in this huge crucible with a tube. The tube is dipped into the bottom of the pot and a vacuum system draws the molten aluminum from the crucible. The aluminum is recovered in a short time. Air is vacuumed from the crucible by a flexible pipe held by an operator. The tube is finally withdrawn and the overhead crane dumps another quantity of alumina into the pot. Thus, the aluminum fabrication process continues uninterrupted. The crucibles filled with molten aluminum are transported to the casting house. Their contents are poured into holding furnaces which have a capacity of 60 tons. In these very hot furnaces, the molten aluminum is stored to await casting. Finally, casting begins. The aluminum is either semi-continuously vertically cast, producing ingots, sheets, or billets, or directly cast into semi-finished products. The cooling of aluminum pieces is accelerated by water sprays. The large rectangular ingots, which can weigh up to 25 tons, will head for hot rolling. eventually leading to fabrication of products such as aluminum foil. From 4 to 5 tons of bauxite have produced 2 tons of aluminum, which in turn produces 1 ton of aluminum. This particular plant produces 200,000 tons of aluminum annually, yet some other facilities can turn out as much as 400,000 tons. When driving, avoiding skidding during a panic stop was nearly impossible. Today, new brake technology, which is computerized and highly sophisticated, is actually making it possible. Brakes are absolutely essential equipment for every vehicle to slow it down and stop. And brakes have remained practically unchanged for the past 40 years. Conventional disc brakes have pads which press against the brake disc attached to the wheel. These pads grip the disc on only 15 to 30 degrees of its circumference. This develops high heat, wheel skidding, and results in premature wear. The new floating disc brakes have 2 pads of friction material on 360 degrees of the disc circumference. When the brake is applied, hydraulic pressure activates the diaphragm, which applies pressure on the inboard pad, which is then pressed against the disc. In this animation, the diaphragm movement is exaggerated. However simple, the design of this brake calls for some complex development steps. It all starts on the monitor screen with computer-aided design. This powerful software creates objects in 3 dimensions which can be virtually manipulated. They then proceed to digital analysis. Here, digital models are submitted to repeated braking to verify that the parts conform to design objectives. The software verifies changes in heat, the effects of vibration, and resistance to breakage. The right choice of materials is critical. The electrical components also have to be created. Here we see the delicate construction of tiny sensors which measure the force exerted by the braking system. The sensor is the main component of the intelligent ABS braking system, which functions more efficiently than traditional anti-skid systems and reduces braking distance. Then it's the fabrication stage of prototype parts which will be tested. The machining of these parts must take into account the requirements of mass production. This high-precision, robotized machining is done by computer-controlled digital machines. A liquid sprinkled on the machine part cools it during the process. The finished parts are precisely measured, then fitted and assembled to form the total braking system, which will be first tested in the laboratory. Brakes in full contact have a friction surface 6 times superior to traditional brakes. The use of aluminum and composite materials allow for a weight saving of 2.5 kilos per wheel. This affects road holding and reduces fuel consumption by 0.1 liter per 100 kilometers. They proceed to power and endurance tests on this dynamometer, in which a brake and wheel assembly act against a large rotating drum. These lab tests are critical since they can detect any defect in a braking system before it's installed on an actual vehicle. To evaluate the power and endurance of the brakes in full application under extreme conditions, they were installed on this Porsche 911 Turbo entered in the Motorola Cup. They proved completely satisfactory, and the Porsche went on to record many wins. Once all validation tests are done, we move on to the next step. Brakes are installed on a production model vehicle. With data systems, engineers can observe the performance of brakes under all conditions, thousands of times a second. Finally, engineers proceed with actual braking trials with test vehicles. All that remains is to produce brakes on a large scale to supply auto manufacturers' production lines. And that's the story of brakes, from original idea to final product. The sound of a car starting is like music to the ears when it's -15 outside. Today's batteries are increasingly powerful and efficient, even at the most extreme temperatures. Kinda heartwarming, isn't it? While dissecting a frog in 1786, the Italian researcher, Galvani, noted that when his scalpel touched a leg muscle, it contracted from an electric current produced. Later, Volta believed the current was produced by the metal instruments, the animal being only a conductor. To prove it, he stacked discs of zinc and copper, connected by conductors, and fabric impregnated with an acid solution. And so, in 1800, the electric battery was born. Batteries power all kinds of electric motors. A new lithium metal polymer battery pack, such as this one, could soon power an electric automobile, as well as a hybrid vehicle. This battery will be made up of 4 components. It all starts with this lithium ingot, which weighs about 5 kilos. It's transformed into a thin sheet by this extrusion press that applies 400 tons of pressure. From it will exit a sheet that's only about 250 microns thick. The whole extrusion sequence is closely computer controlled. Extrusion is now completed. The metallic lithium sheet is the required 250 microns in thickness, or 1/4 of a millimeter. The sheet has to be further thinned. Placed on a roller, it is carried to the laminator. At room temperature, it's thinned once again. In just 20 minutes, the 5-kilo ingot will have been transformed into a thin, 250 micron sheet, some 200 meters in length. This laminator completes the thinning of the sheet to between 20 and 40 microns. The resulting 2-kilometer-long sheet will allow for the fabrication of 210 battery units. Lithium is a soft, sticky metal. For this reason, a polypropylene film has to be fixed on the lithium sheet. Without this protection, the sheet would adhere to itself and become unusable. The sheet will be used to make individual battery cells. Then these cells will be assembled in series and in parallel and inserted into modules of different shapes. To make an individual battery cell, the sheet has to be rolled up. This automated spooling machine winds up the lithium film in 26 revolutions. The wound-up sheet is put into a vacuum oven where the various layers adhere firmly to one another. This step lasts for about 90 minutes at 80 degrees centigrade. Here, a test is made. Using a voltmeter, the battery is checked to see that it produces the required 3.56 volts. Any problem can be detected here and corrected. A final quality check is made with this caliper, which precisely measures the thickness of the battery cell. The battery cells are then stored. Metallic plates are placed between them for the entire storage period. One more step remains, and that's the metallizing of the contacts. The battery cells are sent off to a fabrication facility in this container. The container is robotically handled. First, it's put into a protective tank. Then the metallizing of the contacts is done by spraying on molten metal. This takes just a few seconds, since the metal cools very quickly. The battery is now finished. It comprises 4 elements: lithium, which acts as the anode, a metallic oxide cathode, a dry solid polymer electrolyte, and a metallic current collector. All that remains to be done is the assembling of the individual battery cells into a module. It begins with the placing of individual cells onto one another and isolating them with foam so that they don't touch each other. These red sheets are actually heating elements since the lithium metal polymer cells function at temperatures of between 40 and 80 degrees centigrade. All of the individual battery cells of the completed module are connected to an electronic card located above the module. The finished modules are connected to one another in series and in parallel to form a battery pack, which can be used in an electric automobile or a hybrid vehicle. Here we see these modules of a battery pack for a hybrid vehicle, an automobile that works with a gasoline-powered motor and an electric motor. This prototype battery was created for a totally electric vehicle. It surpasses heavy traditional lead-acid batteries that can't develop the same amount of electrical energy and which have much shorter lifespans. I hope you enjoyed our show today. We wanted to take you behind the scenes to the world of manufacturing. I'm Mark Tewksbury. See you next time on How It's Made.